Good morning. Thank you thank you to moderator and everyone here. In this opportunity, I will present our works in modeling of optimization plastic flow rate in the ozone Para-Xylene simulated moving bed. This work is collaboration between Hangzhou Daehakkyo and Samsung Total. Here is the outline of this presentation. First is the background, SMB application in pH separation, objective of the study, process description, mathematical model, result and discussion, and conclusion. As we know that the demand of PX as the raw material for PET is growing with the 6th annual growth for the next decade. And 60% of the PX worldwide is produced by simulated moving bed technology. SMB is a continuous counter-column multi-column chromatographic process. It is different from the conventional chromatography where the liquid fluid inject to the column with the stagnant fluid and where the weak absorb component will come out first, followed by the strong absorb component. In countercurrent chromatography, the fluid is injected in the middle of column where the fluid and solid are both move in the countercurrent way. As the result, the strong absorb component will go out with the solid direction, and the weak absorb component will go out with fluid direction. The benefit of the countercurrent chromatography is first high driving force, and the second is we can get the product in continuous mode, while in the conventional chromatography we can get only in the batch mode. In their development, there are two types of countercurrent chromatography. It is through moving bed chromatography and simulated moving bed chromatography. Here is the flow scheme of the through moving bed chromatography. We can see that the solid and the fluid has the countercurrent flow. The A is strong absorb component, B is weak absorb component, and here the feed comes to the column and desorbent, extract, and raffinate, which divide the TMB into 4 zones. With each zone has a specific function. Zone 1 function is to regulate absorbent by the desorption of component A, while the zone 2 function is to desorption component B to prevent the B to contaminate the extract port, and the zone 3 function is to absorb component A and prevent the A exit to the raffinate port, and the last is zone 4 is to clean the solvent by the absorption of component B. However, the application of the through moving bed in real is very hard because of the solid circulation problem. That's why the SMB technology was developed. Here is the flow scheme of simulated moving bed technology. It has a very same concept with the TMB, but the solid here is not moved. So the countercurrent way here is simulated by a flow scheme through the port shifting. You can see the extract port is shifting to here next, and so on. And here is the more bigger and detail about the flow scheme. So this is the first shifting, and for the next port shifting, of course, the port of extract will be shifted to here. And here, so we can see what is the problem in the Pradana SMB is the bed line that problem. We can see at the beginning of port shifting, the bed line for extract line is first filled with the previous fit liquid. That's why it will contaminate the extract. And the second is the fluid trapped in the inlet stream also will carry out into the column, which will make the contamination become safer for the next subsequent shifting. That's why the Para-X developed the 3 flushing sequence to overcome this problem that makes the Para-X SMB become H-zone. Here I would like to present the H-zone Para-X SMB in animated sequence, but for not in the real application, the flushing all is occurred in the same time simultaneously. First is line flushing line flushing sequence, we see that the line here first is filled with the composition of previous feed, and this line is filled with the composition of the previous extract. With the line flushing, utilize the internal flushing from this zone 1 to flush this line and through to flush this line. And the second is secondary flushing. Of course, the line will be filled with the fluid from the previous line. So we apply the external flushing with the desorbent to clean this line. So this line composition on the desorbent. And the third is tertiary flushing. We see that this line is first filled with the raffinate, and then this tertiary flushing is not meant to flush out all the bad line, only change this composition to the feed-like liquid. And here the end of the end sifting, for example the third sifting, and here is the beginning for the next sifting. So we can see the extract here is very clean because of it's filled only the desorbent. There is no contamination of feed. And this tertiary flushing purpose is to enhance the recovery. You can see the echelon Para-Xylene SMB become more complex. That's why it needs modeling and more analysis. And this objective of this study is to develop more robust model for commercial X-scale SMB, which considering the specific depth volume calculation for bed head, bed tail, and bed line with the extended Langmuir isotherm. And then we validate the model with the real commercial echelon PIs. Here is the diagram of echelon Para-Xylene SMB. It's a manifestation from the previous echelon that I presented before. It has 24 beds divided to 2 chambers connect to the rotary pumps. The port of desorbent and extra is configured by this. Its bed has bed head connected to bed line, and then but the bed tail only occur in the 12th and the 24th bed. And here is the flow rate streams, flushing and conventional streams. This is the concentration of feed, desorbent, and the secondary flushing. This process we model in 180 shifting, or equal as 20 cycle. With each shifting has a time of 1.15 minutes. Here is the model parameter, and here is the extended Langmuir isotherm parameter. This unit is modeled using the absorptive bed model and non-absorptive bed model for that volume. The absorptive bed is modeled by linear driving force, or LDF. Is the model, and with the extended Langmuir isotherm as absorption equilibrium. And here is the initial condition and the boundary condition. For the dead volume, we model using the diffusion equation here, solved with the MOC. We can see that the diffusion equation here are same for bed head, bed tail, and bed line. However, in the real application, both bed head, bed line, and bed tail has very significant difference in the volumetric flow rate, diameter, and length. This volumetric and diameter will make the difference in Reynolds number, which cause the difference in the axial dispersion constant, while the geometry of this bed will make the axial dispersion profile become different. Here is the proof of the solving PDA for the diffusion equation for the simple condition where the case have the same liquid flow rate, bed length volume, and axial dispersion constant but different diameter. We observe the we observe the pH concentration at the end of the bed line. This is the shifting time. And we can see at the higher diameter, we can get the smoother line, smoother curve because of it has shorter length. But the time here is almost same because of the change in linear velocity. Because of the difference in the profile and the value of dispersion constant, we enhance the model with specific depth volume parameter definition. Here, after we simulate, we get several results, and here is the observation. Here is the same like before, the dynamic pH concentration at the end of extract line during the last shifting. We compare between the optimized flushing flow rate and the non-optimized flushing flow rate. We can see from the optimized flushing flow rate there is no pH here, but for non-optimized flushing flow rate there is the trap pH in the bed line will come out first. And the next is we observe the mean concentration in the extract with versus the shifting number. We can see that in 48 shifting we can get the cyclic steady state because of non-homogeneous bed tail. And in case of optimized flushing flow rate, there are no impurities accumulation. However, in the non-optimized flushing flow rate, there is impurities accumulation. Next is we observe the liquid concentration of 24 beds at the last of shifting. We can see here at the beginning of shifting, middle of shifting, and the end of shifting. We can see the curve is smooth, and that makes discontinuity because of the port shifting. And we can observe there are still high the pH concentration here that make it possible loss through the TFO flushing flow rate. At the end, we get the quite robust result, robust model for commercial Exxon SMB. We compare with from simulation and real plan. From simulation, we get a little bit higher purity but lower recovery. This simulation has quite good agreement with the real plan, but however, we need some enhancement by reconfirm several process parameters such as bed void, flushing flow rate, solid density, and extended long mirror isotherm parameter. And the future work we will use the valid model to find more efficient operating parameters. This is the end of our presentation. This work is supported by Korean Institute of Energy Technology Evaluation and Planning, and thank you for your attention.